Hi Ron, and today we're going to solve dot product of two sparse vectors medium LeetCode problem. It often appears on data science and machine learning interview rounds. So please, if you are seeking a job and want to crack data science interview, please pay attention to this problem. Okay, what is the logic? What is the logic of and task definition of this problem? We have a sparse vector class which we have to write. We have to then initialize our two vectors and create object of this sparse vector class, our custom class, and then we have to calculate dot product of these two vectors. But pay attention, we're not just calculating dot product, we're calculating dot product of two vectors, sparse vectors. What is dot product? Dot product is a mathematical operation that calculates the scalar value obtained by multiplying the corresponding components of two vectors and then summing up those products. And you can see from this example, for example, that we take values one by one, multiply them together, 1 by 0, then 0 by 3, 0 by 0, 2 by 4, 2 by 4, 3 by 0, and we just summarize it into one single scalar, which is our result. What is sparse data? Sparse data is when we have our data, majority of our data consists of zeros. So there is empty data in most cases. And we have to find a solution of efficiently calculating this dot product of two sparse vectors. So let's start. Firstly, what is the most intuitive way to do it? You can explore that we have to just calculate only intersection of our values, because if we have, for example, zeros, it doesn't matter whether the zero from the left side or the right side. We have to only take and multiply values which are non-zeros. So intersection of non-zero values has to be assumed. Okay, the most intuitive way which can come to your mind is just let's iterate from the nums1, and for each nums1 key value, we have to look this key value for in nums2 vector, and if these keys appear, so intersection, it means intersection exists, we can just multiply these values. That's it. So and put it into our dot product variable, which we're going to return afterwards. Let's write this solution. This is not a complicated one, a complicated solution. First, we have to choose what collection we are going to use. I suggest and propose is using tuples, because with tuples you can iterate at the same time by index and values. So you can save it as an index value tuples into our list of non-zero, of all non-zero values, and use these afterwards during iteration, during calculating dot product. Yes, let's implement it. Firstly, let's create our self non-zeros array. Then we're going to iterate over our numbers, which are provided, dense numbers, which are provided for us. If this number not equals to 0, it's not sparse, means we just save non-zeros, we just save this value and its index, corresponding index, as a tuple, and append it into our list. So our structure is list of tuples. Okay, what's in here of calculating dot product? Let's firstly define our dot product variable. Then we're going to iterate over our key and value of our first vector, which is self non-zeros. Just pay attention how we should, how this has to be called. v1 dot product v2. So v1 is going to be used as a self, and dot product is our vector, which is our object vector of sparse vector. So for key to val2, sorry, in here we have to use in vector non-zeros. What we do, if our keys are similar, we check for it. Sorry, what we have to do is just summarize, multiply our corresponding values and put them into our dot product variable. So return dot product at the end. Let's just check it out. It works. What is the time complexity and space complexity of this algorithm? There is a lot of letters and words here, so I'm going to copy it from my notes. The answer to this question, yeah, it's here. This is our iterative solution of calculating sparse vector. The time complexity is going to be for initializing our tuples O n plus m, because we do only two passes over n and m vectors which are of the same size. But I want to pay attention that this is not just I separate them into different variables so to be more clear about time complexity. The space complexity is going to be n plus m, because again we are just iterating one time by of our each do all iterations of one pass over our n vector, first vector, and the same for the second vector, and put this information to our list of tuples. So in the worst case, we're going to end up with n plus m space complexity. But for the time complexity of calculating the dot product, what we do in here, we just multiply our n by m, because we're just for each n we are working. Yes, we're working m times. Then we move to the second m and again take the m times of our of our keys in our keys and calculating our dot product. So this is our time complexity. Is going to be where n and m are non-zero tuple pairs. The space complexity of this dot product method is O1, because we don't allocate extra memory for calculating this dot product. The only one is our dot product variable, which is our result, and this is our, in our case, this is our integer. Okay, let's just put this as a vector, sparse vector v1 task, and just copy again our functions, methods, and that's it. Let's do pass and pass in here. This is yes, I hide this one solution. Let's look at the other solution, how it can be done. The other solution which can come to your mind, or you can see it from the others, is using hash map. This is very efficient solution, but again, we will dive into efficiency of this solution afterwards. How it works. We just firstly initialize our hash map of non-zero values for our two hash maps, for our vector 1, for our vector 2, and then we check if the key of vector 1 exists in vector 2. If they exist, So it means intersection exists, and we can check for whether the key exists in our dictionary in O1 time complexity or for constant time. So it's very fast. If it exists, we just can multiply its values and put these values into our dot product as a sum of all the corresponding values. So let's implement this solution. Okay. What we have to do, let me just copy it from here to save some time. What I'm going to do is just change our non-zeros list to dictionary. What I do, I just also pass it the same way. If n is not equal to zeros, what we do, we just self non-zeros. We put index as our key, and n is going to be our value. Okay. What's next? Again, we initialize our dot product, which equals to 0. Then we iterate over our key and value in our self non-zeros items. Or we can even check for key 1 in self non-zeros. Then what we do for key 2 in vac non-zeros. Yeah, why not? Oh, sorry, if key 1 in exists in vector non-zeros, yeah, sure, this is better, this is right. Let's say it. If it exists, it means intersection exists. So what we have to do, we just have to sum it up with our dot product and sum it up our multipliers, which is self non-zeros key 1 multiplied by vac non-zeros key 1. Yes. I believe that's right. What we do, we just return our dot product. And let me check that everything is okay. I think it has to work. Yeah, it's accepted. Solution, the idea is, I believe, is very, very straightforward. Let's put it as a vector 2 solution, sparse vector 2 solution. Now I'm going again, remove everything, and let's dive into the third solution, which can be provided. For this task, the third solution can be used with help of 2 pointers. What is the idea? The idea is that we have our tuples, and we just go through the left, we initialize our 2 pointers. One left pointer is going to be on the left side of our vector 1, sparse vector, non-zero sparse vector. The second right pointer is going to be on the vector 2. It starts from the 0 indexes, and then we move. We are moving through from the left to the right. If key doesn't exist, for example, in 1, if key doesn't exist for the 1 tuple, but the second tuple has the key much higher than it's in the key 1, we can skip it till our keys matched. So if they matched, then what we can do, we just summarize them multiply its corresponding value and put this into as a summing up to our dot product variable. And we are moving further. Left +1, right +1. This is a standard 2 pointers technique. So let's implement this solution also. What's for this solution? For this solution, we may use the same tuples. So I want to stress that I haven't discussed time complexity and space complexity for solution number 2, but I'm going to return to this solution and explain 2 pointers and hash map solution, time complexity and space complexity together. This is interesting. Why we haven't copied our init. Haven't copied init. So it's here. This is our third solution. Yeah. Some tabs. Let's make it right. Self non-zeros. Yes, we are working through our number array one by one and put everything as a tuples into our list. Non-zero elements, index number. Yeah, that's right. What's in here? The main logic is going to be here, dot product. Let's initialize, as I said, 2 pointers and check while left less than lengths of self non-zeros. We are going to use while loop, and right pointer is less than vec non-zeros. Yeah, we have to stop if our left and or right pointer has moved till the borders of our arrays, so we can stop exploring and return our dot product variable. So we're done. Nothing interesting is going to happen. This is our condition. Let's define our key 1 and key 2 for simplicity variables. Key 1 is going to be self non-zeros L0. This is our key 1. What is for key 2 is the same, but vec non-zeros right 0. 0 is our index. So we're iterating over our indexes. And now we're checking if key 1 less than key 2. Key 2. What we do, we increase our left pointer by 1. If our key 1 more than key 2, what we do, we just increase our right pointer, increment our right pointer by 1. This is logical. What's in here? Otherwise, key 1 equals key 2. It means they're the same. And we can calculate our dot product. We know our keys exist, they intersect, they're matched, and they're non-zero values. So we just simply put our value from the vector 1, from the left pointer. This is our vector value 1, and we just multiply it with vector non-zeros right 1. That's it. Afterwards, what we have to do, we just return our product, dot product. You can even take one more empty line for readability, and that's it. This is it. Nothing hard is going to happen here. The mistake, yeah, let's check it out. What is wrong? I haven't initialized our dot product. It happens. Let's check it one more time. Again, I have found a mistake. When we are in else condition and we calculate our dot product, what we have to do, we have to increase our left pointer by 1 and right pointer by 1, because otherwise we will start, we're going to be in this while loop forever. We go inside, our keys match, we calculate our dot product, and again go into our while loop. Our keys are going to be the same because we haven't incremented our left or right pointer, or both of them, and we are just walking in the circle forever. So let's add I have added our left and right pointer. Let's run it one more time, and that's it. Right now I'm going to submit it. I used some provided for us tests. Let's submit the solution and check if everything works fine. Yeah, sure, it works. Everything works as needed. What I want to discuss right now is time and space complexity of our of solution of number 2 and solution number 3. Let's say put as time complexity of solution 2. This is our hash map solution. And the same I'm going to copy for 2-pointer solution. It's very important right now. It's very, very important. Okay. We have, I have divided time and space complexity, as you have seen before, for initializing our vectors, data structures, and the time complexity for calculating dot product. For time complexity, again, for hashing, we are working one time to generate our tuple of non-zero values for vector 1. Then we are moving and creating the same for vector 2. So total time complexity for creating our hash maps, two hash maps, is O(n plus m). What about space complexity? Space complexity is going to be n plus m, because that's it. We cannot go further. Or OL. OL is just for simplicity, is created here, where OL or O(n plus m) is our non-zero elements. Time complexity for calculating the dot product. In the first case, it was O(n multiplied m. It was not optimized at all. In this case, it's O(n plus m or OL, because we're just taking these two tuples. And yes, or sorry, even it's even faster. It's even faster because yes, we're doing check for O1 time complexity, and we're just iterating over our for loop of our self non-zeros, which is our vector 1. So it's even O(n) time complexity for calculating our dot product. Sorry for this mistake. Store only non-zero elements. But again, we have to check and use, we have to check every key, whether it exists in the second vector. And it's also O1 time complexity, but it's time complexity anyway. It's time complexity. So it's a little bit interesting here. From one thing, I believe we can use O(n) time complexity, but we have to understand that we are checking it every possible time when we are iterating. So it looks like it can be both O(n) or whether we consider it or O(n plus m). Space complexity is simple, O1. What about 2-pointers solution? 2-pointer solution means that we again create our two tuples, O(n plus m, O(n plus m, the same as was before in solution 1. The time complexity of calculating dot product is going to be, we're iterating over our two vectors and with 2 pointers, and increment whether we increment whether left and right pointer. We pass it one time over our n, over our vector 1 or over vector 2. We're doing one pass for each of them. So the total time complexity is going to be on plus m or ol, where on, n, and m are our non-zero tuple pairs. Space complexity is going to be O1. You can also, if you have LeetCode Premium, you can dive into the solution and time complexity provided for us, but it's they use only the time complexity of our, calculating the dot product mainly. For example, this calculating the dot product is OL, and our OL is what is n plus m. This is intersection of our, how to say it, this is our n and m non-zero tuple pairs. What I want to pay attention, yes, this is L plus L2. What I want to stress, please pay attention that there are people which tells that they got this question at Facebook on site or other interviews, and the interviewer didn't accept my hash map solution. He told me that hashing lookups while on surface look efficient. For large sparse vectors, hashing function takes up bulk of the computation, that we might be better off with the first method. So what I want to stress, that this hashing solution, even though it looks like the time complexity is going to be the same, we are calculating hashing and checking for hashing every iteration. It looks like overhead compared to solution where indexes are sorted and goes one by one. In our case, they're sorted. Indexes sorted. So we know, for example, we have fourth non-zero index, then seventh fourth non-zero index, and so on and so on. So just checking it one time, one by one, is not efficient as it can look like. And because it takes time complexity also for calculating the hash. It looks like, let's just provide the example. If we have an array and we just take and look up into what exists in our index in our array, look up in our array, it's very efficient. It's really O1, for example. It's really O1 without some additional overhead. In terms of dictionary and hashing, hash maps, what we do, we just check in the hash, and if this hash exists, we just go and provide the value. So, and this calculating the hash to check whether it exists or not is also takes time, even though it's considered O1 as a super fast. And probably that's it. And this is why a lot of interviewers doesn't accept the hashing solution, and accept only the index value pairs or using two pointer solution instead. And this is why. So from me, it's all. Probably we've done with this really great and awesome product of two sparse vectors medium LeetCode problem. So what I want to say at the end is thank you very much for watching. Thank you very much for listening. Have a happy coding day. Bye.